Hello, my name is Shin. In this video, I will explain the book How to Deal with Variance, Maximizing Quality, which was published by Jujutsu Hiransia in Japan. This time, I made the Windows app for probability distributions easier to use, so let me walk you through the changes. Now you can tweak noise when creating distributions, line up multiple ones to compare, and use graphs for indicators more smoothly so it's simple for anyone to understand and use. I also enabled some extra indicators that were already in the Python library. As an example, I showed how to improve error and deviation scores like in university entrance exams and calculate exact pass rates in different ways. With these updates, I hope more engineers will pick up this method. Here's what's on today's agenda. First, I'll talk about the errors and deviation scores like those used in entrance exams and show how using actual data to build distributions and then calculating percentiles gives different results. A quick note, a percentile means where you stand compared to others. For example, the 99th percentile means your score is higher than 99% of the people, so you're in the top 1%. We'll compare the old method and the improved one using percentiles. The key idea has three parts. Model the spread of data as an accurate probability distribution based on the data itself. Use distribution arithmetic to reflect that shape in the model results. Use those result distributions to make probabilistic judgments with different indicators. And we'll go through three comparisons. Deviation scores traditional normal approximation versus simulated actual distributions, compared with percentiles. Distribution of sums versus sum of distributions. Using entrance exam data to compare several judgment indicators. We also improved the tool to make generating accurate distributions easier. I'll show the updates in an embedded video, along with how they differ from just approximating with something like a normal curve. The software I'll be using today is the Windows executable bungpu.exe, the one at the top address. Percentiles aren't the most precise indicator compared to others we propose, but they're easy to grasp, so I'll start there. Then, I'll explain why only distribution arithmetic can give the correct shape when dealing with sums. Finally, I'll wrap up with a demo video using multiple indicators to predict exam pass rates precisely. First, let's see the error that comes from using deviation scores and standard deviation, and compare it with percentiles based on actual distribution shapes. In entrance exams, scores are usually evaluated by deviation scores. This assumes test scores follow a normal distribution. In Japan, the average is set to 50, and the standard deviation sigma is 10. To show the difference, imagine generating random numbers following certain distributions, treating them as scores from 1,000 students, then calculating the average, standard deviation, deviation score, and percentile. For example, if one test had an average of 40.6 and a standard deviation of 13.7, then a student scoring 65 points would get a deviation score of 66.7, which corresponds to the 96.2 percentile under a normal distribution. But if another test had an average of 59.2 and a standard deviation of 12.8, the same 65 points would only give a deviation score of 54.5, or the 67.4 percentile. Next, we'll use the published software on handling variation to calculate percentiles from the actual distribution of the same test scores, and compare the results. When you double-click bungpu.exe from the repo I mentioned earlier, you'll see a screen like this. Pick a menu option, load your data or enter values, then hit execute to get a graph. The screen has three sections, top, middle, and bottom. The top and middle are for setting distributions or boundaries, and the bottom is where you choose operations or evaluation methods. Each section has a menu top right, a button bottom right, and an input field bottom left. For example, to create a distribution from a data file, go to Input 1 in the top section, choose Data File 2 from the menu, then type in the file name along with options like rows to skip, which column to use, number of bins or dx equals 4 bin width, and click the button. A graph will appear, yellow bars are the histogram, and the blue curve is the kernel distribution. From here on, all calculations are based on that kernel distribution. The kernel distribution traces the histogram. By setting the bandwidth kh equals, you decide if it follows the bumps closely small value or smooths things out large value. For example, if you add kh equals 3 and click, you'll get a smooth distribution, which is then used for calculations. To calculate a percentile, in the Input 2 field middle section, enter the boundary value and +1 or -1 to choose which side of the boundary to calculate. For example, typing 65-1 calculates the probability of scoring less than or equal to 65. Then in the bottom menu, select %4 and hit execute. The graph shows 94.4%. If you remove kh equals 3 and run it again with a different bandwidth, the result becomes 94.5%. So the bandwidth error is only about 0.1%. Let's take a look at the results from the two methods. Test 1, if you scored 65, the percentile based on the standard deviation comes out to 96.2%, while using the kernel distribution tool which takes the actual shape of the data into account gives 94.4%. Both use the same 0.1.csv data, but the standard deviation is a bit higher, about 2%. That's just because it assumes a normal distribution. You can try it yourself, the data's in the repo. Test 2, for the same score of 65, the standard deviation method shows 67.4% and the shape-aware method shows 70%, so the standard deviation is about 2.6% lower. Again, this comes from approximating the data as a normal distribution. The data is in 0.2.csv, so feel free to check it out yourself. For tests 3 and 4, we looked at distributions with bigger skew. Both datasets have an average around 50 and a standard deviation of about 15, so a score of 35 should be around a deviation score of 40, and 65 should be about 60. Percentiles using normal distribution, 35 16.1%, 65 83.5%. Percentiles using the kernel tool accounting for actual shape, 35 11.6%, 65 92.2%. The error from assuming a normal distribution jumps to around 5 to 10%. This shows that using deviation scores or standard deviation always comes with unavoidable errors. When the error is this big, it's hard to say the quality is really guaranteed. In real product or system development, multiple sources of variation usually exist. In those cases, the error can get even bigger. Next, we'll look at distributions where multiple variations are included, using the same test score example. Let's think about variation when multiple sources of variation are involved. Here, we assume the total variation comes from the sum of several factors. One thing to consider, when summing two datasets, sometimes you can just look at the sum's distribution, and sometimes you need to consider the sum of each distribution separately. Case 1, sum's distribution is enough. For example, if you want the total score distribution for 1,000 students combining English and math, the sum of individual scores gives the total distribution. But even here, if you want to make future predictions, it might be better to consider the correlation between the two distributions and calculate the sum using a distribution operation with the correlation. Why? Because the actual sum distribution only reflects the observed data combinations, while many other possible combinations should also be considered. Case 2, sum of each distribution is needed. Suppose you have 1,000 English scores and a separate 1,000 math scores. If the two datasets are independent, no correlation, you need to compute the sum as independent distributions. This kind of sum might not make much sense for evaluating test scores, but in design or data analysis, this is actually more common, yet people often handle it like case 1. This sum distribution is similar to what you get using the Monte Carlo method. In my view, Monte Carlo results often don't guarantee the true distribution shape. Next, we'll check how much the resulting distributions differ between these two cases. Here, we'll actually calculate the difference between the sum distribution and the distribution of sums using the English, math, and Japanese scores. Data setup, we use the file .5.csv, which has 3 columns English, math, Japanese for 1,000 students, along with a file containing each student's total score. First, generate distributions from each subject and calculate the sum assuming the distributions are independent. Then compare this sum of distributions with the actual total scores. In the tool, specify the file, number of rows to skip, columns to extract, and bin width. For English column 2, specify column index 1. For math column 3, specify column index 2. After checking each distribution, English distribution looks like this. Math distribution looks like this. Click Execute on Add to get the sum of distributions. The console will show z0 equals x plus y, and the result is stored in z0. Next, extract Japanese scores column 4, index 3 and add it to z0 by clicking Execute. The console shows z1 equals x plus y, stored in z1. This z1 is the sum of the English, math, and Japanese distributions. Compare this with the total scores from the file. Each student's total scores are in column 5 index 4. Select existing distribution for z1. To display multiple distributions on one graph, choose Graph 2 in the lower menu and click Execute. Blue distribution 0 equals actual totals. Red distribution 1 equals sum of individual distributions. Observations: the actual sum distribution is much narrower than the sum of distributions, about 50 points narrower from min to max, and 100 points narrower overall. This shows that when multiple sources of variation exist, 1000 data points aren't enough to get a proper distribution. For a single source of variation, 1000 points are fine, but multiple variations require massively larger data. The practical solution: generate individual distributions from smaller datasets and then use distribution operations to calculate the resulting distribution. This gives much more accurate results. So far, we've shown that using distributions based on actual data improves the accuracy of percentiles in distribution calculations compared to just using standard deviation or post-calculation distributions. In other words, doing distribution operations and then making decisions based on the resulting distribution improves calculation accuracy. Here, I'll explain an advanced way to use distributions as decision-making indicators, taking percentiles a step further. Percentiles give probabilities by measuring the area above or below a certain threshold. The second method extends this idea. Instead of fixing a threshold, we compare two distributions probabilistically. For example, the left distribution equals test scores of a general group ability distribution, the right distribution equals scores of people accepted to a specific university target distribution. By computing the cumulative distribution of the target scores and multiplying it with the ability distribution for each score, the resulting area represents the acceptance rate. This gives the probability that the left distribution exceeds the right. In the tool, you can compare distributions from 1D up to 3D in any direction. Using the third method, balance search, we can calculate acceptance rates more accurately when additional data is available. Example: right distribution equals accepted scores, left distribution equals rejected scores. Create a cumulative distribution for the right moving right, and for the left moving left. For each score, divide the cumulative probability of the accepted distribution by that of the rejected distribution to get a precise acceptance rate. This indicator tells you exactly which distribution dominates at any point. Further, if you treat these distributions as physical quantities instead of probabilities, you can search for equilibrium points of opposing quantities. For example, in economics, you can find the precise equilibrium of supply and demand. For more details, see the separate video on supply-demand balance design. The fourth method, proximity, calculates the probability that two distributions are within a specified distance of each other. This is done by shifting one distribution and summing values for all parameters within the distance range. Originally designed to calculate the probability of two objects touching in simulations, there isn't a clear application in the education/testing field. Next, I'll show practical examples using the second and third methods with the tool. Let's explain how to compare two distributions using the tool's new feature. Input 1, specify point1.csv, which has test scores for a general group, and add extraction conditions. Input 2, specify point2.csv, which has test scores of students accepted to a specific university, and add extraction conditions. For both menus, select data file 2 for the top and middle sections. The distribution for input 1 looks like this. The distribution for input 2 looks like this. In the bottom section, set the cumulative direction to +1, choose Compare in the menu, and click. The comparison graph will appear. In this case, the probability that the general group exceeds the accepted group scores is 15.5%. This type of distribution comparison has many applications in design and analysis. For a deeper explanation of cumulative distributions and multidimensional extensions, please refer to the book. Next, we'll use balance search between two distributions to calculate the probability of passing for a given score. Here, we improve accuracy by using both accepted and rejected student data. Input 1, point1.csv scores of rejected students. Input 2, point2.csv scores of accepted students. Set kh equals 3 for a smooth distribution. In the bottom section, -1 means the cumulative distribution of input 1 is taken in the minus direction. +1 means the cumulative distribution of input 2 is taken in the plus direction. Set the target TG to 40. SHW equals 1 searches for the intersection of the two cumulative distributions. SHW equals 2 calculates the values of the two cumulative distributions at the target and computes their ratio. Since we calculate the passing probability from the ratio of rejected to accepted distributions, we use SHW equals 2. For the top and middle menus, select Data File 2. Choose Balance 2 in the menu and click to display the graph. The graph shows a line at score 40. X beta ratio equals 84.8%. Y beta ratio equals 15.2%. This means the probability of rejection equals 84.8%, and probability of passing equals 15.2%. Compared to the earlier result using only accepted students, this is slightly different, but considering rejected students makes this result more reliable. Let's explain how to handle multidimensional distributions in balance search. For example, estimating the pass rate based on 2D distribution of English and math scores. For 2D distributions, in the top and middle extraction settings, enter the columns to extract and the number of bins for both x-axis and y-axis. For cumulative distribution direction, in 1D, we just used +1 or -1. In 2D, specify a vector and an angle range. Set the x, y, and angle in brackets, and provide two sets corresponding to the two distributions. Also, enter x and y values for the target TG. Click to display the two 2D cumulative distributions along with the TG point. The graph shows what percentage influence each distribution has at the target point. You can drag, zoom, and move the graph to change the view, and you can save the graph for later use. Let's explain how to handle multidimensional distributions with percentiles. Generating 2D or 3D distributions. Specify a file that has at least as many columns as dimensions. For data extraction, use brackets to specify multiple column numbers and the number of bins for each. In the menu, select Data File 2, and enter the file name and extraction conditions. Click Select File to display the distribution. In 2D, the graph shows contour lines. To capture finer details, set a smaller kh value. For a smoother distribution, set a larger value. Setting the boundary for percentiles. In 1D, we used single brackets. In 2D or 3D, use double brackets, specifying points on the boundary and the perpendicular vector x and y values. This vector indicates the direction for calculating volume. In the bottom menu, select percentile 4 and click. The 2D distribution graph appears. You can drag and rotate the graph to get a clear view and save it. On the graph, the volume below the boundary, i.e., probability below the boundary, is shown as 93.4%. Next, let's explain how to specify multiple boundaries when using percentiles. Using percentile 4, in the middle section, you can create multiple sets inside double brackets, separated by commas. For each set, specify the points and perpendicular vectors. This lets you define multiple boundaries. Click to display the distribution between the two boundaries. The probability between them is shown as 65.1%. Here, by specifying 2 points and opposite vectors, we calculate the volume inside parallel lines. You can define any number of boundaries with any angle, and the tool will calculate the probability enclosed by them. Summary. Deviation scores used to indicate rankings from test scores are calculated from the standard deviation, which assumes a normal distribution. Comparing them with percentiles calculated from the actual data distribution, deviation scores can have errors of a few percent up to about 10%. Using the variation handling tool, which processes the actual distribution shape precisely, can improve this accuracy. When multiple sources of variation affect the data, the distribution after standard calculations may be softer and less accurate. In such cases, distribution operations are effective, as we demonstrated. The tool, which runs on Windows, provides an environment to handle variation rigorously. Using the indicators proposed in the variation handling method, you can make precise predictions of pass rates based on real data. For example, comparing two distributions can give the probability that a group exceeds the accepted distribution. You can also calculate exactly how much influence accepted versus rejected distributions have on a student's score. This concludes the video. Below, you will find the links to tools for applying this method, the book purchase site. The tools I put on GitHub are free for learning purposes, but must be the same version of Python as described in env.txt. Install the same version of Python in a virtual environment such as Anaconda. If you need further assistance or if you are going to make commercial use of the software, please contact me at the address written in the README license. Thank you very much for watching.